Good morning. It's really great pleasure and very big honor to give talk in this auditorium here. I was a little bit surprised when the organizing committee asked me to give this talk about the mathematical modeling. But now later I understood that because of the place where I'm working now, the name of this laboratory is mathematical modeling. Yeah. And you see, I prepared this 50 slides, but now I understood that there are too many formulas. Maybe I'll begin just with some explanation. I tried to find what does it mean, mathematical modeling, and I used computer, internet, I used Yahoo, and there were more than 40 million. This is mathematical modeling. It's a mathematical reasoning which expresses some non-mathematical phenomenon. If this formula expresses some mathematical phenomenon, it's not mathematical modeling. It's just mathematical result, for example, or mathematical theory. Yeah. And I was told that in the audience will be people who are not mathematicians, chemists, biologists, and so on. Because of that, maybe it would be not so interesting for a mathematician. Please criticize me each time when you decided to do so. But it's a little bit detailed explanation, but for the people who doesn't know mathematics. And I would like to say that maybe next page. I mentioned this book of Sir Isaac Newton, Philosophiae Naturalis Principia Mathematica. Why this book is the first? The mathematical equations, how to say, mathematical reasoning was used in ancient Egypt, for example, during construction of the pyramids. It's well known. But the real mathematical modeling began from this book, where it was a explanation of the law of gravity. You know this story, maybe I'll just repeat a little bit again. Just 330 years ago, in some cafe in London, there were three famous persons. There were Robert Hooke, you know Hooke's law, you know microscope, he was inventor of microscope, and cells, he used this word cell in biology. Second was Christopher Wren. Christopher Wren, he was architect, you know St. Paul Cathedral in London. It was built by the Christopher Wren. And third was Edmond Halley. Halley, he was very young. They were about 50. Young was less than 30. Edmond Halley, you know, comet Halley, Halley's comet, Halley, different pronunciations here in Great Britain and the United States. Like Bernard Shaw said that everything is the same in the United States and Great Britain except language here. And you see, these three guys discussed the problem about the gravity. It was well known that the force decreases on the big distance, but what's the law of decreasing? And it was understandable for everybody at that time that it's inverse square of radius of the distance. I can explain why. Because you see, if there is a sun and there is some planet which is rotating around the sun, there is a gravitational force. It attracts this planet to this sun, and usually they think that sun connected with all this planet by some threads. The force is thread-like. And how many threads? For example, n number of threads. And let's suppose that this disk has the area 1. Yeah. In this case, how many threads will connect this planet with this sun? It's very easy to check. N divided by the area of the sphere, yeah? And the sphere is 4 pi r squared. That is the law. In case if we are at the plane, it will be 2 pi r. It's c over r. It's understandable that after integrating that the Newton potential is 1 over r, and in planar case it will logarithm. Yeah. But it was only, how to say, conjecture, it was hypothesis. It was necessary to prove. And what necessary to prove? The planet are rotating around the sun following some circle. But Kepler showed that it's not circle, it's ellipse. To understand ellipse with very small eccentricity, how to say, it was necessary to have a very good measuring of the location of these all planets. And the best calculations were made by Tycho Brahe, but 150 years before it was made in observatorium of Ulugh in Samarkand. You can find in internet, in Wikipedia, everywhere that only after 150 years the results of Ulugh were, how to say, repeated in the observatorium by Tycho Brahe. And Tycho Brahe was very happy because near to him was Kepler. And Tycho Brahe himself does not understand the meaning of this experiment, of these observations. And Kepler found that it was the ellipse. The orbit of the planet is ellipse. Till now it's very difficult to understand why Kepler decided that it's ellipse. And the question was, if the force is decreasing like inverse square of distance, in this case the orbit must be ellipse. And Hooke said, I know that, but I do not know how to prove it. And the youngest Halley, next day, it was 330 years ago, in 60, well, maybe 64, yeah, 64, yeah, sorry, 84. 16. And next day, Halley went to Cambridge, met Newton, and asked him, if the force is like this one, what will be the orbit of planet? And Newton said it would be ellipse. And Halley was surprised, and he said, wow, why do you know that? He said, I calculated it, I proved it. And Halley asked him to write this proof. And you see, if we have distance, the second derivative is for example, that according to second law, is it equals to force, yeah? And if force is C over, after the calculations, you can find that R is some constant if we use the polar coordinates. 1 plus epsilon cosine phi. If epsilon is small, it's ellipse. That's a solution of this equation. Epsilon depends on C, on M, and so on. And if epsilon is equal to 1, this is parabola. And if epsilon is greater than 1, this is hyperbola. This is a solution, very simple, but it's enough to write it for 1 or 2 days. But Newton, he understood that the proof will be real proof at that time if he followed some books of Euclid. And he gave the proof without derivatives, very big book. And he explained that we will use some special law, the first law that it's well known, first law, second law, and he used that. He explained that this law were used and discovered by Galilei. Yeah. He wrote this book for 2 years. And what is interesting, we know only these numbers, and then we found that it was ellipse. You see, we know if the force is decreasing as inverse proportional to square of the distance, in this case the trajectory will be ellipse or hyperbola and so on. This is written, oh sorry, in the previous year, Formula 1. We know F it means the force or the distance, and we try to find U is an orbit, A is a model, it's some differential equation and so on. And only after Newton we can not only to explain some phenomenon but to predict the future. This is most important thing. And after that, there was something like euphoria. Everybody decided that if you have mathematical model, we can calculate everything. Laplace said that if I'll know all the initial coordinates and initial velocities, I can calculate everything, the prediction of our universe and so on. Yeah. It was announced by by Adamar. Adamar in 1970, during the international Swiss Mathematical Society, the Congress, but it was International Congress, and he explained what does it mean, the good mathematical problem or good mathematical model or well-posed mathematical problem. If the solution exists and is unique. And he gave an example. I show that just this example. It's example of Adamar. This problem is not good from this point of view. We can find some solution. Initial data exponentially goes to 0, but the solution exponentially grows. It means that you can calculate all this data f very precise, but the result will be absolutely different. And he said that this kind of problems are ill-posed. And there is no such a physical phenomenon which may be described by such a model. But to his surprise to everybody, just this problem was used in electromagnetic prospecting. You see, how to understand what's inside the Earth. You can dig it, but the best thing is just to measure the electromagnetic wave. And this electromagnetic wave depends on somebody which is inside. But you can measure it only on the surface. This is just this electromagnetic wave follows Laplace equation, and it means that it's a Cauchy problem for Laplace equation. But calculations, it was impossible to calculate until the Second World War, when the computer were invented. Yeah. Next, it's another problem. Don't pay attention to these formulas. Just the problem. It was studied first by Tikhonov, who proved this Tikhonov product theorem about the topological product. He was very young. He said to me that he was very young in 1930. He was 24 years old, and his dream was to visit Leningrad, St. Petersburg, but he had not enough money. And one friend of him said that, you see, there will be the international conference in geophysics, or maybe not international, but some conference in geophysics. If you will write some paper or if you announce some report in geophysics, they will pay everything for your trip, for your accommodation, and so on. And he decided to write some paper about this. We know the temperature of the Earth now. Using this heat equation, we can say what will be the temperature after 1 year, for example. Is it possible to explain what was the temperature 1 year before or 1,000 years before? And he wrote this paper. It was ill-posed problem. And he was invited, and he visited St. Petersburg, and later he became the academician, corresponding member of academy by the Department of Geophysics, not mathematics. Yeah, and he continued his study, some geophysical problems, including electromagnetic prospecting and so on. And but calculations were impossible, he said. It was very strange, especially it was during the Second World War, when the German troops took all this part of Ukraine and Russia, where in this part were a lot of oil and gas, and they need to find it in Siberia using this electromagnetic prospecting. But it was very difficult to use it because the calculations were impossible, because the problem is ill-posed. And after that, he understood that it's necessary to find some regularization. And next problem, it's just explanation. Adama said that these problems are not important, but after that we find a lot of important problems which are, that's just explanation why this inverse problem for heat equation is ill-posed. It's understandable from physical point of view. What does it mean, the temperature? Temperature is the mean value of the velocity, of square of velocity. Kinetic energy is V square. For example, we have the box with two parts. All the gas is in one part and nothing in another. The temperature in box number 1 is very high, and the temperature in the box number 2 is 0. Then I open, for example, I will open this partition, and the gas will be uniformly distributed in this big box. And the question is, yesterday this gas was on the box number 1 or number 2? It's almost impossible, yeah, to give the answer. This is inverse problem for heat equation. It's understandable that it's ill-posed, yeah. But sometimes it's possible. For example, if I'll open and after 1 hour, for example, in the beginning there was a temperature 40 and there is 0. And after some minutes, the temperature there will be 30 and there is 10. You can understand that it was on the first box, yeah? Or for example, there is 25 and there is 15. It's possible to give the answer. It depends on time. It depends on how precise you have the measuring. And the precise measure, precise sensors. It's a big data nowadays, something like that. Yeah, I was asked to explain what does it mean big data. I used internet. I tried to find big data. The answer was about 200 million files, and I said, this is big data, yeah. Yeah, and next problem is, that's the reconstructing of something shape, how it's oscillating something if you know only some pictures. No, maybe it's not so interesting. This problem was studied by American mathematician Fritz John, and he had an excellent, proved excellent results. Yeah, that's explained about rational, and some ratio might be rational number or irrational number. From physical point of view, it's nothing. For example, if I'll say that a solar system is stable, if the ratio of radius of planets is a rational number, it's not stable if it's irrational number. It means that if one electron came to our solar system, after that it will be unstable. It's very strange, yeah? Yeah, okay. And yeah, this is from mathematical point of view, it's very interesting. We study this equation, and usually A, good operator, it's understandable. If F is more smooth than U in this case, but the problem is worse when the operator A is better. What does it mean? Because inverse operator in this case is unbounded usually. And to find a solution, it means to find inverse operator, a in the power minus 1. A in the power minus 1 is good if a is bad or something like that. Especially integral equations. Just, yeah. You know this Radon transform. It was introduced 100 years ago. You know the integral, it's an integral geometry. You know the integral along all line. Can you find the density? Can you find the function? It's possible to find according to Radon. Why is this problem became important? It's understandable, yeah. We have something, we integrate over all the lines, or these lines. This integral is, shows the density of something which is inside. It's necessary to find it, location. And using only, there is some, for example, X-ray which is coming in, and this is outside. We measure only this difference. And this difference shows it's an integral. And integral is integral on, we integrate the function which is unknown. Can we find this function? It's a very important problem, but it was impossible to solve it without computers. Now it's well known as a computed tomography. Yeah. And this problem concerned with the integral equation of the Fredholm integral equation of the first type, how to say it. It's ill-posed problem. And just using this computer, you cannot find this solution. What does it mean, the computed tomography? You know X-rays. X-rays gives the picture, and this like a photographer, and you look to this picture. But computed tomography, we solve some integral equation. Instead of the integral equation, we used algebraic equation. We find the solution, and we construct the graph, drive the graph of this solution, and this graph is this picture. Yeah, it depends on how precise you find this solution. Maybe I will give some. For example, if you find a solution that the density is over there, you see it's a very big mistake for a surgeon, yeah? Where to open this skull, yeah? Yeah. It's for mathematical point, it's just a little bit mistake, yeah, but and radon, yeah, just there is a connection with my report, with my talk, which I made the day before, because you see, he suggested to use Fourier transform, an inverse Fourier transform. This is spectral expansion. And there are two phenomena which has the influence to this problem. For example, Gibbs phenomenon. Gibbs phenomenon shows that if we have some jump, the partial sums are not like this, but they have this jump too, additional, about 18%. It's a Gibbs phenomenon. And it means that instead of this line, it will be this line. You see, it's mistake because of Gibbs phenomenon. It's necessary to avoid it and to use some special methods. And just about Pinsky phenomena, if there is some this shape of the boundary, the influence may be over there, and the picture will be different as a real picture. And again, some method of regularization can avoid it. Yeah, okay. And yeah, I would just like to explain a very simple example. Very simple mathematical example. A computer never solves the integral or differential equation. We, instead of this integral or differential equation, we use some algebraic equations, maybe 1,000 or 10,000 unknowns and 10,000 equations. But just we consider only two equations with two unknowns. You see, every coefficients are determined except we are measuring something, and we are measuring the data which I called lambda. And this lambda we can measure with precise. The problem, if we measure it precise, the result will be okay. That's just example. We know that lambda is approximately 200. If it's 200, the result x, I write here, x is 5, yeah, and y is 0. It's okay, and that's enough for us. But I know that there is some error. Plus minus 1, it's less than half of percent, and because of that I try to find if lambda is 201, I decided I try to solve it again, and in this case x is 30, but mistake only half of percent, and y is minus 37. I know that something bad is over there, but computer shows no, it's over there, yeah. Again, I tried to find it instead of 200 plus 1, I used 200 minus 1 lambda. And in this case, x is minus 20. You can calculate it yourself. And y is 37. No, next calculation shows no, it's not here, it's over there. It's our recommendation for surgery. Yeah. Maybe because we measured it not good. Okay, we will measure very precise. Plus minus not 1, but plus minus 0.1. The error is not half percent, it's 0.05%. 5 over 100, yeah? Very small error, very precise measuring. And the result, again, if it plus, in this case, x is 7.5, and y is minus 3.7, yeah. But if we will take a little bit less than 200, in this case, x is 2.5, and y is 3.7. And what we say to surgeon after that? We do not know what's the real result. I don't know. Nobody knows. And this is explanation why the mathematical modeling sometimes is more complicated than it seems. This problem really was solved in 1960s when the computed tomography was invented, and using this method of regularization. I'll explain. It's understandable because the determinant in the, according to Cramer's law, determinant in the denominator is almost zero, yeah, and because of that. But all the numbers are integral, yeah, in this equation. All the numbers are integral. And there is one line and there is another, and this is solution. But if the second line is almost the same, in this case, it's very difficult to find. It would be better to find a normal solution. It's a solution which is near to zero, to origin. But this normal solution not continuously depend on the coefficients. Why? We have two similar lines. In this case, we look for normal solution. But if we change a little bit the second line, the intersection might be everywhere. And in this case, computer will give the precise solution, which is very far from the normal solution. And what's the purpose of regularization? Instead of this line, we will consider the stripe, yeah, strip or stripe, how to say it, yeah. And we'll look at this intersection of these sets and find something inside this sets. That's it's not interesting maybe from a mathematical point of view, but I'll just show. Yeah, there is some calculations. Yeah. Sorry. Oh, and there is a result which is given by regularization. No, sorry, not this. Yeah, 3.43, 2.32. This is how to say. This is a real value of the solution. Yeah. Very far from this. And I think that this solution is something like that. And it is used by modern computed tomography. Just this explanation. You see, we have a system of two equations. The second equation is the same as the first. Just multiply by square of 2. Yeah, it will be the same. But computer doesn't know that it's the same, because computer cannot calculate this square of 18, 32, and after calculation they became different. And the more precise you calculate it, the more more how to say far from the real solution it would be, because the mistake can send this intersection to every point. It was made using computer with calculations 100, 200, 300, and 400 digits after the comma, yeah. And the result very absolutely different, without regularization. You see, I decided to change a little bit the topic because it was explained to me that there will be not only mathematicians, and some people, they do not like to use mathematics. And I would like to give at the end of my lecture only 3 examples how dangerous to avoid mathematical formulas, not to use mathematics. 3 well-known examples. You can find in the internet everywhere. But in addition, I give some mathematical explanation. Usually they just show these pictures without any explanation. Just sometimes with a wrong explanation. I try to give the correct explanation. Yeah. This is. You see, that's example number 1. Hyatt Regency walkway collapse. You see, you can read it. It was awful thing. It was the worst thing in the United States before the, this September 11, 2001. 140 people were killed. What happened? You see, in this Hyatt Hotel, they made these 2 walkways which were hanged, something like that. Sorry. Maybe all the values. Oh, yeah. Thank you. The suggestion was that's a ceiling, that's one walkway, it's another walkway. And there is, oh, it goes here. No, it's okay now. But it's very difficult to make these very long pieces of this construction. And the constructor asked, maybe you change it by this one. And no differences, but it's just easier to make it shorter. Yeah, and it seems no calculations, but you see what's the difference? I go to the mountain and we use some rope, and I use this rope and my friend too, but instead of that he said it's rope too long, maybe I'll use your leg instead of this mountain. You see this connection not to this one but to this ceiling, to this walkway. And this part there is only P, the force, and there is 2P. Is understandable or no? Because it takes not only this one, but this one too. Not additional explanations, yeah? It's a very simple mathematics. And what was the result? This one. There was some suing, some penalty after that. A lot of people died. Yeah, just you see explanation. On the left side, that's first the idea. On the right side, it was made by this picture. It's understandable, yeah? It's one example of lack of mathematics, how to say. Very simply, it's possible to solve this problem by the students of high school, maybe elementary school. Number 2, corner crack. It's a little bit more difficult. No, I will use this part, yeah. You see, oh, yeah, let's go. We consider this plate, and the vibration of this plate is very good. The solution is very smooth. The vibration of this plate must be smooth too, because we just in this domain the solution is very smooth, in this domain very smooth too. The difference is the solution of this state will be very smooth. But the calculations show, you see, if we calculate this, the real equation is the equation of the fourth order is a biharmonic equation. But this is a very good mathematical model too. Just we try to find this solution inside the angle. Inside this angle. And there is a solution. And this angle is mu pi, this angle. If mu is, there is written this solution, yeah, okay. If mu is 1/2, it's this case. You see, and a solution is not bad. X squared minus y squared. It's an analytic function. That's okay. If mu is 3/2, what's the difference now? This is 3/2. In this case, the solution is r in the power 2 or 3. And the force is derivative, it's a gradient. It's, the force is, I write here. Oh. Force, you see, now R is in denominator. It's very easy to show. All there, yeah? You can see it. The force is a gradient, is a R in the power minus 1 over 3. It means that R, when R, what does it mean R? R is this distance from this point. Here it's okay, but here, when you come near to this point, the force became very, stress became very strong. Infinity. It's very easy to calculate to everybody who knows partial differential equations. It's for the students of the second year of education in the university. It was very strange that nobody can took it into consideration. Yeah, that's surface stress, yeah? It's understandable. The difference, again, here, everywhere is everything okay, and here, where is the bad points? These 4. Is that understandable or no? Because this part is just here. Yeah? Or whatever. The first jet craft for a passenger was made in Great Britain in 1949, just after the Second World War. I think it was a project of some bomber, but look to the windows. And for 4 years it was okay. But after 4 years, the first accident, 2nd May of 53, 43 people were killed. But at that time there was a thunderbolt. And they decided that, because of weather. Just after some time, again, in Italy. First was in India, second in Italy. And 35 people were killed. There were no thunderbolt, the weather was very nice. But they decided maybe something happened just after 1 month or some months. Yeah, just, you see, less than 1 year, 3 accidents with comet. And the next was 21 passengers were killed. And they stopped it and they began to investigate. And they found, they put it into a pool filled by water and changed the pressure. You see, the pressure, why it was not discovered before jet planes? Because before there were no difference between the pressure inside the airplane and outside. But when they used the jet planes, there was a big pressure inside and not a big pressure outside. It was some oscillation of this airplane, yeah? And they checked it. Because of this metal, it was possible about 3,000 oscillation, and after that it will be broken. 3,000, it means about 3 years of flying. And it happened just after 3 years when they were made. You see, this is calculations when we consider this. Yeah. In this case, the solution is very good and very smooth. It means that there is no stress at all. It's understood. If this hole is round, there is no stress. And please check. On the top is the first model, and on the bottom is a new model of airplane. Just compare the windows. And no accidents after that. And the next jet crafts, which were made by Boeing, by Lockheed, by some other companies, they used it. They used this result of the investigations which were made in Great Britain. It's a mathematical mistake. Not mathematical, they didn't calculate it. After that, there were a lot of calculations now. You see, I defended my thesis in Institute of Applied Mathematics in Moscow. And some people said it's not necessary to make some model, just to use the, how to say it, try and this, yes, trial and error, yeah. But sometimes it's impossible, because the well-known things which were made in this institute is, first was A-bomb, second was space investigation, how to make this A-bomb using this trial and error, yeah. Only calculations, yeah. calculations of critical mass and so on. And the third example, at auto oscillations. You see, we consider the if we consider this wave equation, we suppose that f is depending on time as cosine omega t. There is a solution. It's very easy to check. UK is the eigenfunctions. It's easy to check. It's understandable. When omega coincides with some point of spectrum, the denominator will be 0, but the numerator will be 0 too. It will be some like a derivative. And this is the result. T in front. What does it mean, T? The amplitude began to grow. It's well known as a resonance. Every time you construct something, you try to avoid this resonance. What does it avoid? To find to make some constructions which eigenvalues are different from the frequency of the outer force. It's possible, yeah, but you see, let us consider the case where there is no frequency at all. There is no oscillating force. Just constant g of x, y. This is solution. You see, in this solution, there is a cosine t2. Oscillation may be made. It's not necessary to apply the oscillating force. You know this example of the violin. When the musician is playing the violin, he applies the constant force, but we have some oscillations. The name of this is, it's not resonance, it's auto oscillation. Especially if the nonlinear case, it's understandable. They were discovered mathematically about 70 years ago. Yeah, it was well known at that time. In 1930, it was known. In 1942. But nobody paid attention to that. Self-oscillations, yeah. You see, there are some self-oscillations like this. And I'll explain, I will give you one example concerned with Tacoma Bridge, just a second. This bridge was made from steel. Washington State. It's on the northern part of United States. There was a dog inside this car, and this dog didn't want to leave this car. Finally, the swinging road of suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog. You see, just from, yeah, okay. Yeah, there is a description. 7th of November, 1940. And there was, you can find a lot of explanations, but almost all of them are wrong. They said that there was a resonance. To make the resonance, it's necessary to wind go periodically with oscillation. That wind was very strong and stable, constant. And however, there were such oscillations. What's the reason? I was very proud that I found myself the explanation, and just repeating this, how to say, rehearsing this talk. The day before yesterday, I found just the same explanation in internet. Yeah, it's a pity. Yeah. sometimes you are very proud that you are first, and then somebody will explain that you are not first, not second, maybe 100,000 your number is. Yeah, but however, I would like to share with my explanation. You see, this is about the, how to say it, carrying power or carrying force of the wing. If we have wing like this one and there is a wind, there is nothing, yeah. But if the wing has this shape and there is no turbulence, it means that the air goes in this way, and where the velocity is higher, on the top or on the bottom. It's understandable. To have no turbulence, the velocity here, the speed is higher, because the distance is longer. And there is a law of conservation of energy. What does mean energy? Potential plus kinetic. Kinetic is the speed, and the potential is the pressure. It's constant. It means that if the velocity is kinetic energy higher, it means the pressure is not so big. Yeah, comparing with, there is the pressure from atmosphere, this one, and there is a big pressure. And after that, the wing began to go up. That's the explanation of the flying of airplane. Let us suppose that we have two wings and this one. In this case, it will go up. And let's suppose that wings are very small. Again, it will go up. There is some force additional. We need to look to this bridge again. What is the difference between other bridges which are very stable? The difference is, so there is a, how to say it, parapet, or some, for the pedestrian there is something made. And usually it's made transferable for wind. But now it was solid on the both sides. Only this difference. And this difference was the crucial, yeah, because now there is additional force. This constant force which produced the auto oscillation. You can say, no, it's a force not so big, but you see this wing can, how to say, can lift the airplane with 200 passengers, altogether 200 tons. And comparing with this wing of airplane, this bridge is a huge wing. And because of that, this force was very big. And again, yeah, this is explanation, like two small wings. And if we consider, we can use the same expansion, and usually we can take only the first one. This is the first one. This is the first mode. There is mistake, mu11, yeah, mu11, sorry. Cosine, because boundary conditions, you see, this is a bridge. This is y, and this is x. No, it doesn't matter, x. And here the conditions, Dirichlet conditions, the solution is 0. And here the conditions are Neumann conditions, the normal derivatives are 0, yeah, because there is nothing on the both sides. And the solution in this case will be sine, you see, or maybe vice versa, sorry. No, it's okay, yeah. Sine. No, I cannot understand. Maybe another picture, maybe this one. Yeah. 0 here, 0 here, and the normal sine over there along this x and cosine along the y, yeah, okay. Cosine pi x over 2a and the sine pi 2a, it means this is a and this is b. In particular, if y is 0, just in the center, the solution is 0. It means that the center of bridge is not moving. And this professor who escaped from his car, he used just this straight. I'll show again. Sorry, if I have not enough time, maybe, yeah. Just a second. Yeah. Just look, he was choosing this central part of the bridge because it was moving not so hard, because the solution is the odd function and it is 0 in the center. Just. You see, compare with sides and with center. Yeah, and the professor, maybe not in this movie, professor was going just along this 0 movie. Yeah.
Only at 35 miles an hour wind is blowing, but this apparently is...
Maybe it was not, it was a different movie, I forget. This is professor who was invited to explain all this. Yeah, he tried, you see, he tried to use this lane, the near to, yeah, near this white lane. Yeah.
Fortunately, the only casualties were a car stalled on the bridge and a dog.
Just a second. Yeah, that's it.
We'll take a few minutes for some questions if you have some.
Yeah, thank you.
All right, in the absence of questions, then let's thank our speaker.
Thank you.
I grew up with this book on the Silk Road, this beautiful illustrated book with Tashkent and Samarkand, and I was really excited. Well, anyway, back down to reality. And so my talk is about, so this slide is where we're going to end up. But just to, so this is kind of starting at the end of the talk, but just to give sort of experts some idea of where we're going. I'm interested in nodal sets of eigenfunctions. So nodal set, it just means 0 set. And eigenfunction means eigenfunction of the Laplace operator. So here, this is the Laplace operator, and phi j is the jth eigenfunction. And then lambda j squared is the jth eigenvalue of the Laplacian. And the eigenvalue problem is that the Laplacian of the eigenfunction is the eigenvalue times the eigenfunction. And so this equation makes sense whenever you're on a Riemannian manifold of any dimension. And we're interested in the study of the 0 sets. But before, I want to spend actually half the talk just motivating the problem, why we're interested in eigenfunctions and their nodal sets. So I want to go back to even an earlier era of quantum mechanics than in the previous talk, namely around the turn of the 19th century, when atoms were not even fully understood to be physical objects. And Bohr and Rutherford were, creating a modern theory of atoms as kind of electrons going around a nucleus. So what I'm calling here the Bohr models, and this is not exactly historical, but the basic thing that almost everybody learns in high school is that you can visualize a hydrogen atom by having a nucleus consisting of a proton and having an electron orbiting around it. So this is, the picture is just a picture of a 2-body planetary problem. And just the Kepler problem. And that's well known. In fact, it was the reason Hamilton invented Hamiltonian dynamics was just to convert Newton's laws into a first-order system with twice the number of variables. So the Hamiltonian for this problem is just the usual Newtonian form where you have kinetic energy and potential energy, and the potential energy is just the Coulomb law. So this is not a gravitating system because the attraction is electric rather than gravitational, but this original model is kind of very classical physics that in some sense Newton would understand. But it can't possibly be right, because unlike a gravitating system, if an electric charge is orbiting a nucleus, it's going to emit electromagnetic radiation, it's going to lose energy, and it's going to spiral into the nucleus in a split second. So the atoms couldn't possibly be stable if this picture were truly correct. Yes?
May I object to unlike the gravitational. The gravitational do the same things too. They emit gravitational waves. That's why the pulsars have their frequency that shifts. But it's simply much slower process.
Okay. Anyway, so this from the experiments, it did seem as if there's a proton in the center with an electron orbiting around it. And so in some sense, the picture looked correct, but it can't be just this simple two-body problem. So Bohr comes up with an old quantum mechanics, which tries to explain how to rescue this picture. So I'll put it this way. He rescued the picture by saying that the electron can only exist in certain orbits, which are said to be the Bohr-Sommerfeld orbits. They're like the ones satisfying a quantization condition. And the electron cannot just continuously move into the center because it would have to jump from one orbit to another. Well, that's an old quantum theory from like 1910 or something. And it would be impossible to make that a real theory of atoms. For one thing, except for a hydrogen atom, you would never have such a simple classical dynamics again to work with. So in 1926, omitting all the other players in the game, Schrödinger proposed a theory which is still accepted as being correct, which is the Schrödinger equation. So Schrödinger quantized the original problem, which means that he replaced the kinetic energy by the Laplace operator. He replaced the potential energy by multiplication by the potential. And so he replaced classical mechanics by this eigenvalue problem for a Schrödinger operator. So here the Laplacian is the sum of the squares of the second partials. I'm thinking about a flat Rn. And Planck's constant, which is going to play a very important role in this talk, because we're interested in the behavior as h goes to 0. And in our problem, it'll be equivalent that the energy goes to infinity. So we're interested in this eigenvalue problem. And phi j here, depending on what the Hamiltonian is, I'm making an assumption that we have a discrete spectrum of eigenvalues, and then we have an orthonormal basis of eigenfunctions. So this was a rather amazing paper. I reread it recently and found it almost incomprehensible, even if you kind of understand what the theory actually is. How he came up with this equation is kind of miraculous. Okay, so nowadays we have all these quantization theories trying to make it seem reasonable, but it was a huge leap of faith and one of the kind of great triumphs of mathematical modeling. So what is it good for, this equation? Well, we're replacing classical mechanics of an electron orbiting a nucleus by an eigenvalue problem. Now, why is that helpful for us? Our original problem is that the classical mechanical picture would not lead to stable atoms. They would just disintegrate instantaneously. But here, the time evolution is given by the propagator. And the propagator in quantum mechanics is the exponential of the Hamiltonian, but it's e to the minus it over Planck's constant times the Hamiltonian. So this I is very important because the Hamiltonian is a self-adjoint operator, and it has real eigenvalues. So when we take e to the minus it times it, the eigenvalues become purely imaginary. So when you take a function of an operator, here an exponential, all we do is have the same eigenfunctions, and we just take the function of the eigenvalues. That's just a spectral theorem. So the eigenfunctions of the Hamiltonian automatically satisfy this eigenvalue problem for the unitary operator which evolves the dynamical system at time t. Okay, now one of the fundamental interpretations in quantum mechanics going back to 1925 is that the only quantities that are observable, I think that Svetlana was just explaining to us what is and what isn't observable in quantum mechanics. But anyway, the only observable quantities always are quadratic in this eigenfunction and involve it times its modulus. So one is the probability density of finding a particle at a point x. That's just phi j of x squared dx. Or more generally, we could take the diagonal matrix elements of an observable A, a self-adjoint operator. So we take the operator A, apply it to phi, and then take the inner product with phi. And what happens is that if you replace phi by its evolution at time t, that just means replacing it by the right-hand side here, which has this unit complex number times phi. So if we take this and we put it in here and we put it in here, the phases cancel out because over here we have the phase, and on the right-hand side we take the complex conjugate, and it cancels out. Just the way that it would cancel out if we took the modulus squared over here. So in other words, these modulus squared and these diagonal matrix elements are constant in time. Okay? So this looks simple, but it's a fairly amazing fix for the original problem. We just made observable quantities independent of time, so that as far as observations go, this eigenfunction is in a stationary state. The observations are not changing in time. Okay? So what just happened is that we just fixed the problem that a moving particle will radiate energy, spiral into the nucleus, and be unstable by making the state of an electron a wave function, phi j, rather than a point moving around. And it evolves by linear algebra. It just evolves by this propagator. And instead, we don't have points moving around the nucleus. We have L2 functions, phi j, which are evolving, the wave function of the particle. And it is evolving by this linear algebra formula. And we see that it's not going to be falling into the nucleus. In fact, in terms of all observations, it's not moving at all. So it resolves the problem of how an electron could be moving and standing still at the same time. Okay, so there's a kind of amazing piece of mathematical modeling. So at the same time, by the way, what I'm reviewing here is exactly paragraph 1 of Landau and Lifshitz' book on quantum mechanics, if you ever read it. So this is usually the way that a nice quantum mechanics book will start off, by trying to motivate why quantum mechanics was invented. So if you're following it, quantum mechanics resolves this puzzle, or at least creates a mathematical model for how an electron can be moving and stationary at the simultaneously. However, in doing that, it replaced something we understand very well, which is geometry, the stuff of our ordinary lives, with the eigenvalue problem. So the eigenvalue problem, we usually encounter it in a course on linear algebra. And this is somehow infinite dimensional linear algebra. And so we replace geometry with linear algebra. So it resolved the problem, but it creates a new one, which is how do we have any intuition for the states of an electron and how it's moving if what we're given is an eigenvalue problem? How are we supposed to have any kind of intuitive understanding of what the eigenvalue problem means? So then this is basically the whole motivation for this branch of mathematics that I work in, is how do you visualize eigenfunctions? That's your picture of what an atom looks like, so how do you actually use it to picture it? So let's look at the simplest case. It's almost the only case among atoms where you can actually picture it. And this is a hydrogen atom, the original problem that we're dealing with. So you notice that we have the eigenfunctions depend on the eigenvalue, Ej of h. And so we have in this case, these are called the bound states of the hydrogen atom, and we have just a discrete set of them. This is the ground state over here. So I'm drawing you a picture of 25 states of the hydrogen atom, eigenstates of the hydrogen atom. This is what's called the ground state. It has the smallest energy. And it looks as if it is concentrated very much where the yellow light is. That's the nucleus. So the wave function, if I take the square of phi, this is where it's largest, right here at the center at 0. And then when you see this little red thing, it's where it's pretty large, and then we just darken it out once it's so small that you can't see it anymore. And now these over here, this is like a first excited state, and the size of the atom starts growing, but it still looks spherically symmetric here. This is the next excited, so it's probably the same eigenvalue, but this time it has some angular momentum, and you can see it's kind of lined up around this axis. Here's another one that's lined up on a horizontal axis. Here's a more excited state, which is even larger and which is rotationally symmetric. So if you study these pictures, you can, in fact, this is basically what a first-year graduate level text in physical chemistry will start out doing, is giving you the different eigenstates of a hydrogen atom and trying to make physical meaning out of these pictures. Try to be able to look at the picture and say, what is the angular momentum of the hydrogen atom? What is this energy? What is the angular momentum around the z-axis? You can picture it from these. Okay? So this is great for the hydrogen atom. If that were the only Schrodinger equation, life would be very simple. So what we were just looking at are called intensity plots. So you just darken in the region where the square of the eigenfunction is large. And here are some other intensity plots that I was able to get off the web. And once again, you see this is the ground state. So the phi squared, for the lowest eigenvalue, the eigenfunction is concentrated, in a kind of spherical blob around the origin. Here's the next excited state. Here you have some angular momentum around different axes, and so forth. So this is terrific for the hydrogen atom, but just try to imagine what's going to happen if you start dealing with a more complicated Hamiltonian. You'll never see such simple pictures again. This is another example where the eigenfunction is very large at the top here, very large at the bottom. This is actually what's called a zonal spherical harmonic, and then it's kind of fairly large around the equator. So these are called intensity plots. Now, at the other extreme, just one remark. This is the most interesting type of thing you can associate to the eigenfunctions, in the sense that if I wanted to know one thing about an eigenfunction, I would like to know where is it largest, and what is the set where it's largest. How large is the measure of the set where it's largest? How large is it where it's largest? Because this is where the particle is most likely to be. So a good theory of eigenfunctions should be able to give you something about describing the set where the eigenfunction is as large as it can possibly be, as well as some statement about how large it can be. So at the opposite extreme are what are called the nodal sets, which is the subject of my talk today. So the nodal sets are just the opposite thing from the intensity plot. We draw in, unfortunately I couldn't get very good pictures for the hydrogen atom, but the nodal set here are these white planar things, or here there's a white little cone thing. But these are the sets where the eigenfunction is 0. So the intensity plot marks in where it's most likely to see the quantum particle, and the nodal plot is marking in where it's least likely to see it. I'd rather know where the electron is most likely to be, rather than where it's least likely to be. But the reason my talk is about nodal sets is that there are essentially no rigorous theorems, about where the eigenfunction where it takes on its largest values. There are very few theorems even about how large it can be. So we would really like to understand where it's large, but what we're sort of able to understand is where it's small, where it's zero. And we get some good idea of the shape of the atom or the electron by knowing where its nodal, what its nodal set is. So roughly speaking, the problems that I'm describing in this talk has to do with trying to figure out where the nodal set is and how the nodal set is distributed. Can we at least understand the geometry of the nodal set? Can we at least figure out where the particle is not going to be? So this is, of course, a mathematical talk, but actually this is of some current contemporary interest among experimental physicists. The original Bohr model for the electron, for a hydrogen atom, is it's a toy mathematical model, and people had, actual data on the frequencies of light given off by the hydrogen atom, but not so much about the shapes of the actual, about the shape of the hydrogen atom. Now these are just last year experimenters with the leader at Stodoina have actually put a hydrogen atom under a very strong microscope, and you can actually see the hydrogen atom, and in particular you can actually see the nodal set patterns. So actually, even though I've looked at these pictures before, I can't say I really see them all that clearly, but maybe this is like a nodal set pattern here. But anyway, if you look at their paper, they will guide you through it. And so trying to see the nodal sets of a hydrogen atom is actually contemporary experimental physics of atoms. Now, before getting into something so complicated as nodal sets for Schrödinger eigenfunctions or Laplace eigenfunctions, let's just go back to undergraduate school for a moment, where we first hear about nodal sets. And this is, in some sense, the picture that people like Rayleigh and Schrödinger and Bohr had in mind when they were, and even up to the contemporary era. This is the picture that they're trying to generalize. Namely, the first eigenvalue problem in PDE that we ever see is the vibrating string. So here I said drum and membrane in higher dimensions. So a vibrating string is a one-dimensional Schrödinger equation, just phi double prime is minus eigenvalue times phi. Here I put Dirichlet boundary conditions. So as we all know, the eigenfunctions for this problem are just the sine of nx. So this is where the term nodes came from. So in the physics literature, the zeros are called, this is the ground state of the vibrating string. Here's the first excited state, second excited state, third excited state. And as the eigenvalue n, or the frequency, increases, each time you develop one more node, right? And as well, there are these things called antinodes, which are the local maxima, rather than being the zeros for the vibrating string. So this gave people the idea that as the energy goes up, the number of nodes goes up. You can use the number of nodes to measure the energy. As well, these antinodes are the critical points. Somehow the energy should be measured by the number of critical points. That's the kind of naive picture which is part of the contemporary PDE to try to establish any kind of aspect of that. It's still really completely unknown. Now that's not just true for one-dimensional, for y double prime is minus lambda y, but for any one-dimensional Sturm-Liouville equation. So if I take a one-dimensional Schrödinger operator and I write it down, then the eigenfunctions are just functions on the real axis or a finite interval. And here I did the one, this is the most famous one, it's called the harmonic oscillator, where the potential is x squared. Here's the potential. And once again, this is the ground state. This is the square of the ground state. And it has no nodes. It's like a Gauss. It's just a Gaussian. The first excited state has a node here. These are not nodes. It's just exponentially decaying out here. Then the next one has 2 nodes. The next one has 3 nodes. And so that picture of as the eigenvalue goes up, you get one more node each time, one more critical point, is true for the harmonic oscillator in one dimension. I might add that we're only talking about real zeros here, but there are some recent theorems, Hamid Hazari, for example, and other people, which describe complex zeros of these equations. So there's still contemporary interest even in the one-dimensional problem. So what do we do in higher dimensions? Well, the most simple situation is where you can separate variables. So for example, if instead of being on an interval, if we were looking at a vibrating square, then the simplest eigenfunctions are just obtained by writing products of one-dimensional eigenfunctions. So it's just the function is f of x times g of y. And then to find the zeros of a separated eigenfunction, it just vanishes if either f vanishes or g vanishes. And then you end up with a checkerboard pattern. So this is what happens. So just to see if everybody is awake, how often do you think that the eigenfunctions could be written as a product of a function of x and a function of y? Like, what? Almost never, right? And it probably indicates something about the domain here, the region here. What do you think is a word that would go along with having eigenfunctions where you can separate variables? It's a completely integrable system. So this happened with the hydrogen atom, and it happens with the square. And that gave people a little bit of hope that in higher dimensions you can imitate the one-dimensional picture. However, it's very naive because it's going to be impossible unless you have a completely integrable system. It's not even possible for every completely integrable system. So once again, this is like the ground state where you have just a function 1 in each variable. And then here's one where in the vertical direction you have one node. The horizontal direction you have no nodes. And so forth. Here in the horizontal direction, f has one node, g has one node. And as you take products like this, you develop these checkerboard patterns. But however, this is really completely unrealistic. It's not even realistic on something like a square or a flat torus, because you can have multiplicity for the eigenvalues. You can have more than one eigenfunction with a given eigenvalue. And if you take linear combinations of these separated solutions, you will end up more with a picture like this. This is what the nodal set will look like of a typical eigenfunction, even on a square. One of the things you see in this picture rather than this one, you notice that we have like the nodal line self-intersects here. So these self-intersection points are called singular points. And people are so used to seeing these singular points, either for a hydrogen atom or for a square, that it may become as a surprise that in the generic case there are no singular points of any eigenfunction at all. So these are extremely unusual pictures. If you develop your intuition based on these pictures, you will probably get completely misled. And this is a much more generic picture of what a nodal set actually looks like. So what do we really want to do? So I started off by saying that the Bohr model gave us a beautiful geometric picture of the states that an electron can be in, namely electrons going around certain orbits which are quantized. However, we can't imagine how you can generalize that to anything beyond the hydrogen atom. How would it work for a helium atom or a lithium atom? How would it work for just any Riemannian manifold? So Schrodinger says we have to look at the eigenvalue problem, and then we're stuck because we don't understand how to interpret visually or intuitively what an eigenfunction is giving us. So what we would like to do is understand the nodal sets, and we'd like to understand them for general Schrodinger operators or general Laplace operators on Riemannian manifolds. And what we would like to do is to relate the geometry of the eigenfunction, the geometry of the nodal set, to the dynamics of the geodesic flow. Okay, how the geodesics move around on the manifold. So first of all, it's actually not obvious why there should be any relation at all, even to experts in the field. It's not at all obvious why or if there should be any decent relation between the nodal sets of an eigenfunction, where the particle is least likely to be, and the way that geodesics move around on the manifold. Geodesics on the Riemannian manifold is classical dynamics. So this is like the picture of the orbits. We want to kind of recover the relation between the orbits and the eigenfunctions. So now I'm going to begin a little more formal presentation where we go over the definitions of the eigenfunctions, the geodesic flow, and we get to the problem, the new results. So, you know, if you're on a Riemannian manifold, compact or non-compact, there's a second order elliptic operator associated to it called the Laplace operator. It's very natural because if you just integrate the gradient squared of the function over the manifold, there's always a second order operator where the integral of the gradient squared is the operator times applied to f inner product f. So this is, I wrote it in local coordinates. If you're not familiar with it, this is not the best, this is not the global definition. It's just locally it looks like Euclidean, but here this is the metric tensor. We have G lower ij is the metric tensor, and G upper ij are the inverses, and this is the determinant of G lower ij. So it looks similar to the sum of d squared by dxj squared, but a bit more complicated. And we go back, we're interested in an orthonormal basis of eigenfunctions. So if you are studying eigenfunctions, I use a somewhat unusual notation where I write the eigenvalue as lambda squared rather than lambda, which saves me. So lambda to me is the important thing, it's the frequency. And this is an orthonormal basis, and once again I'm interested in the zero set. So as I said, the Bohr model, the beauty of the Bohr model is that it proposes a very close relation between the classical mechanics of the Kepler problem or the classical problem and the quantum mechanics. So what we were really interested in is trying to relate classical mechanics, which is geodesics, to the shapes and sizes of eigenfunctions of the Laplacian. So the size is measured by LP norms of the eigenfunction. The shape is going to be measured by the nodal set. And we would like to relate the shapes and sizes of the eigenfunctions to the classical dynamics on the Riemannian manifold. So to date, I've only succeeded with this in two extreme situations, namely where the geodesic flow is very chaotic, and on the other hand where it's completely integrable, which means it's very predictable. So almost essentially nothing useful. Well, a few results are known, but these are where most of the results are. So let me define the nodal domains. In fact, I think I'm going to put this up as a picture because we might have a manifold like this, and then we look at phi j is equal to 0, and so it breaks it up into lots of little nodal domains. Who knows what they look like? So these are called the nodal lines, or the nodal set. And inside here, this is what's called the nodal domain. So if I take M, and I remove the nodal set, this is the union of the nodal domains. So these are like the intervals between the nodes in one dimension. These are the nodal domains. So generically, 0 is a regular value, which means that the level set, the zero set of the eigenfunction, let's just think in 2 dimensions, will be smooth curves, closed curves. You get self-intersections when 0 is a singular value. So here's some 2-dimensional checkerboard type pictures once again of nodal domains on a sphere. This is once again separation and variable situation on a sphere. And we get these kind of these pictures. So here's a linear function on the sphere, and it has a negative region and a positive region with a 0 set along this meridian geodesic. Here we have a more excited eigenfunction. This is an eigenfunction on the sphere, and so it separates variables. So we have 1 or 2 nodes in the vertical direction and maybe 1 or 2 nodes in the horizontal direction. This over here is what's called the zonal spherical harmonic. It's rotationally invariant. So here it's positive, here it's negative, here it's positive, here it's negative, here it's positive. And in between the positive and negative regions are the nodal lines where it's 0 and so forth. So those are sort of going back to these very simple pictures. But this is much more realistic. You know, the eigenvalues of the Laplacian on a sphere have huge multiplicities, and so you can take random linear combinations of the eigenfunctions of this separation of variables type, and when you take random combinations, the nodal sets will look like this. So here again, the white regions where it's positive, the black region is where it's negative, and the nodal line is the boundary between the positive and negative regions. And so you can see that the nodal set in general is very kind of uniformly distributed on the manifold. Almost none of the details of this picture are understood. There's some rather recent brilliant work by Nazarov and Soden on how many nodal domains should actually exist for a random spherical harmonic. In fact, it's a subject of quite active interest, and Sarnak and other people have also recently posted a paper on the subject, and Bourgain. And it's so trying to understand, you know, how many of these nodal domains there are and where are they is even for random spherical harmonics is a very active subject right now. So here are some classical results. So first of all, I should have stated the conjecture first. So it's a very natural conjecture based on the one-dimensional picture that no matter what metric or Riemannian metric you have, there should exist some sequence of eigenfunctions where the number of nodal domains tends to infinity. You remember in one dimension, as the eigenvalue goes up, then one more node. So the number of nodal domains goes up once each time. So you may not have a linear growth rate of the number of nodal domains with the eigenvalue, but at least you would hope that the number goes to infinity. Well, it was actually proved by a student. It was actually proved by a student of Hilbert and Courant, and it's in their book from 1930s or whatever it was, that the number of nodal domains does not necessarily increase with the eigenvalue. So a student of Courant and Hilbert, found sequences of eigenfunctions just on a square where the number of nodal domains was less than or equal to 3. And then Hans Levy, who was actually a co-author of the second, I believe he was a co-author of the second of the Courant and Hilbert books, but he was in any case a student in the Hilbert and Courant circle, generalized this in a really complicated paper in the 80s and showed that on a round sphere you can find sequences of eigenfunctions where the eigenvalue tending to infinity, where the number of nodal domains is just 3. So in other words, the number of nodal domains does not have to go to infinity with the eigenfunction. There's a similar thing about the antinodes, which is that you might expect the number of critical points also to increase with the eigenvalue. And a counterexample to that was found by Jacobson and Nadirashvili, who found examples where on a torus where the number of critical points and consequently the number of nodal domains stays bounded by 10. So Yao had actually made the conjecture that the number of critical points should tend to infinity with the eigenvalue. So recently he has reposted his original problem list, and I corrected his conjecture to be the following: that for any metric there's some sequence of eigenfunctions where the number of nodal domains tends to infinity. Now let's just pause for a moment, because if anybody in the audience has studied nodal domains or eigenfunctions, this conjecture looks so easy that I encourage you to try to prove it. The first time I saw this, I thought, I mean, how hard can that be? Otherwise, it's saying that the number of nodal domains of the eigenfunction is bounded by 10 for all the eigenfunctions, no matter what eigenfunction you pick. It has no more than 10 nodal domains. That sounds impossible for a generic Riemannian manifold, and I thought I tried writing down different types of proofs, and there's a catch in all of them. So I don't know. But this conjecture seems so simple to prove. I mean, you don't have to know anything. I guarantee you there's nothing known that's going to help you. So if you just think of something, you know, that's a very nice elementary conjecture to study. Now, before I discuss results, I wanted to mention a problem which sounds extremely hard. It's more like science fiction than it is like a real problem to work on, which is to figure out how the nodal hypersurfaces are distributed on the manifold. And so what do you mean by that? You mean that you take a continuous function on the manifold and you integrate it over the nodal set. For example, this could even be the characteristic function of a nice domain in the manifold. It doesn't really have to be continuous. And then try to figure out how this integral behaves as the eigenvalue goes to infinity. So it's known that the length of the nodal line in dimension 2 is roughly of size lambda j. So this ought to diverge like lambda j. And if we normalize by dividing by lambda j, we'd like to know what kind of limits this has. So these are just what we call limit distributions of nodal sets. Okay? And once again, we'd like to know how does it reflect the dynamics, although there's no kind of obvious reason why it should. And here's a conjecture that I just call a generic physics conjecture, that at least if the metric is real analytic and the manifold is ergodic geodesic flow, then if you integrate a function over the nodal set and divide by the frequency, then it should tend to the surface, it should tend to the average value of the function. So this is just saying the nodal set should be uniformly distributed on the manifold if you have ergodic geodesic flow. So I proved this in the random case. If you look at random combinations of eigenfunctions rather than eigenfunctions, this is almost certainly true. But trying to prove it deterministically for the actual eigenfunctions is, I think, kind of a science fiction problem. But these kinds of pictures, there are many pictures like this in the physics literature. This is an example of a billiard table where the dynamics, billiard dynamics, is chaotic. Anytime you have these concave sides to it, the dynamics is very chaotic. So it's going to bounce off the side by the law of equal angles, and the billiard trajectory is just going to become uniformly dense in this thing. Now what we're actually looking at is the nodal sets of an eigenfunction, and it looks just as uniformly distributed. So there's no obvious reason why uniform distribution of geodesics should have anything to do with uniform distribution of zeros, of eigenfunctions. It's just, but physics intuition tells you that that should be true. So I'm just restating the problems. We were interested in two problems. How many nodal domains does an eigenfunction have? Does the number of nodal domains increase with the eigenvalue? Does it tend to infinity, at least for some sequences? And the second question is, how are the nodal sets distributed on the manifold? So the first result I want to, well, this is a little background on number of counting nodal domains. So if this is an orthonormal basis of eigenfunctions, and n of phi is the number of nodal domains, if you're on a sphere, genus 0, then the number of nodal domains is just the same thing as the number of connected components of the nodal set, if you have a regular value, if the components are all regular. So Courant, many years ago, proved that the number of nodal domains for the nth eigenfunction is always less than or equal to n. Okay, so that's just an upper bound, and the Yau-type problem is to get a lower bound. Okay, and we know that there's not a universal lower bound by the results of Levy. So I think I'll skip that. So here's the new result. So this is a recent work with Jun-Hyuk Chung, and it goes the following. So I'm going to state, maybe I show you the picture first. So we're going to be working on a Riemann surface like this. So this is called the hyperelliptic Riemann surface of genus 2. And this surface is the complexification of a real algebraic curve. So it has a symmetry made by complex conjugation. Complex conjugation is going to map the top to the bottom. So the real curve is the boundary over here and also inside over here. And you have a complex conjugation mapping the top of this pretzel to the bottom of the pretzel. You also have another seeming symmetry from left to right, but we're not going to be using that one. So this is called a anti-holomorphic involution. Involution means the square of the map is the identity. Anti-holomorphic is like complex conjugation. And the fixed point set of this involution is this apparent boundary that we're seeing here and also here and here. That's called the fixed point set. Now, one thing you notice is if I remove this fixed point set, like if I remove this, so here's a good exercise for coffee time. Suppose you just snip along the fixed point set here. You'll see that you disconnect the pretzel to two pieces. So that's called a separating fixed point set. So now I go back and say what the theorem is. Suppose you have a Riemann surface with this orientation reversing involution, and where the fixed point set is separating. So just think of it as one of these hyperelliptic Riemann surfaces. Then if you're given any negatively curved metric on the surface, which is invariant under sigma, that's hardly any condition at all. You can always average the metric over sigma. So if you're given any negatively curved metric for which sigma is an isometry, then for essentially the entire sequence of eigenfunctions, the number of nodal domains tends to infinity. Okay, so not only are we proving that the number of nodal domains tends to infinity along some sequence, we're proving that the number of nodal domains tends to infinity along the entire sequence. Now, I might have to puncture out a sparse subsequence, but I'm not going to emphasize that. So on the one hand, these surfaces are rather special topologically. Yeah, they have to have this involution. On the other hand, the metric here is extremely general, any negatively curved metric. And in fact, the only property of the negative curvature I use is that the geodesic flow is ergodic. So we really are relating, what we're proving here in essence is that the ergodicity of the geodesic flow is forcing the existence of a lot of nodal domains for excited eigenfunctions. Okay, and as I'll mention in a moment, it's not just true on these surfaces. So here I stated the theorem sort of formally. We have a compact, negatively curved, smooth surface. It has an orientation reversing involution. The fixed point set separates. And then for any orthonormal basis of either the even or odd eigenfunctions, that is, they either are preserved by the involution or switch sign, one can find a full density subset of natural numbers so that the number of nodal domains tends to infinity. Now, here I mention even and odd eigenfunctions, but actually for the generic choice of the metric, all of the eigenfunctions are either even or odd. So this is not a restriction at all on the eigenfunctions for the generic metric. So, in fact, I'm going to make that point here because it's rather important. For a generic sigma invariant metric, all the eigenfunctions have multiplicity 1, and the eigenfunctions are either even or odd. So this parity restriction is not a restriction at all in general. And just to give a formal definition, when you say that a subset of the natural numbers has density 1, it means that if you count the number of elements in the subset less than n and divide by n, then it tends to 1. And I already went through that. So here's another example of a Riemann surface to which it applies. So the second thing is that the same result is true without any symmetry assumptions at all on a domain with a boundary. So if I take a surface with curvature less than or equal to 0, and once again, this is going to cause ergodicity to occur. That's all we're using it for. And I take out a disk from the surface, then I get a very chaotic billiard table, which is called the Lorentz-Sinai billiard table. And what we prove is, once again, that for the Dirichlet or Neumann eigenfunctions on the surface with boundary, then for almost the entire sequence of eigenfunctions, the number of nodal domains is tending to infinity. So here's what that looks like. Here I've taken a square. So this could be here's a torus. And when you take a disk out of a square, you take it out of a torus, once again, the billiard problem becomes hyperbolic because you took out a convex body. So that means that it's a very dispersing billiard, and the billiard trajectories bounce off in a very dispersive way. So that's, we're proving it for the white domain minus this yellow thing. Now, I should mention that before our result, and influencing our result, was a paper of Gosh, Reznikov, and Sarnak. So they proved a theorem of a related kind, but using many number theoretic hypotheses. So they proved it for very special eigenfunctions called the Moss-Heck eigenfunctions. They're working in this geometry and what's called the modular domain. That has a left-right symmetry as well, which they use. Okay, so they're using, theirs is a non-compact surface. And they counted the number of Nodal domains. And what they find is that if you just count the number of Nodal domains intersecting a compact segment, then they get a power law lower bound. So that's a really quite remarkable result. We're just proving that the number tends to infinity. They're getting a power law lower bound, which is really quite nice. In fact, I'm sort of stunned that I cannot get a power law, but that's life. I can probably get a logarithm of lambda, but at the moment I can't get near to a power. So that's very nice. But in revenge, we do not have to assume anything such as the Lindelof hypothesis for Rankin-Selberg zeta functions or whatever. We don't have to restrict to these very special things called Heck eigenfunctions. Our results are PDE results which hold for very general metrics. So to end my talk, in fact, I guess it's over in about, what, a couple minutes or something. I wanted to come back to the other problem, which uses similar techniques. But I mentioned the science fiction conjecture that if you want to find out how the nodal set is distributed, you integrate a function over the nodal set, divide by the square root of the eigenvalue, and it should tend to the volume average of the function. This is uniform distribution. So the funny thing is, which may be of interest to people in the several complex variables section, I can't prove this or disprove this, but I can prove the same thing in the complex domain. That is, if I analytically continue the eigenfunctions into the complexification of the manifold, and if I look at the complex zero sets, then I can actually prove this. So for some reason, maybe not unknown to people studying real algebraic versus complex algebraic geometry, the complex nodal sets are way better behaved than the real ones. So here are the two rigorous theorems. This is a now pretty old theorem. I have to assume that the manifold is real analytic because I want to analytically continue eigenfunctions into the complexification. And once again, I assume that the geodesic flow is ergodic. And then for all but a zero density subsequence of eigenvalues, if I take a function on the complexification of the manifold and I integrate it over the complex zero set instead of the real one and divide by the square root of the eigenvalue, I get a limit formula. In fact, I realized that you can even go onto the boundary, of this complexification, and you get exactly the same thing. So what's happening is that the nodal sets have the desired distribution law on the boundaries of these what are called Grout tubes. They actually have exactly the physics conjectured behavior if you go into the complex domain. And then in a more recent paper, I proved the same thing for intersections of geodesics and nodal sets, but maybe I will not go into that one. So I'll stop here.
Questions?
Yeah.
Is there anything for non-compact manifolds?
I would expect almost everything I say to have an analog for a good analog for non-compact manifolds. It's just you have to break things up into different types of problems. For one thing, we use ergodicity a lot. So where is that going to come from if you have a non-compact manifold, right? We also well, we have the problem with the eigenvalues, but we could just let this. So we, in other words, I would expect that there's a rich theory there, but nobody has really, I haven't really worked on it. I would say, like the fact that you have a continuous spectrum really isn't going to be that big a problem. We'll just take the generalized eigenfunctions and look at their nodal sets and, look at it in a compact region. But we need dynamics in these arguments. I didn't really go into how we do that, but it's all about looking at the zeros of eigenfunctions in the ergodic case and getting the ergodicity to force lots of zeros to occur. When you count nodal domains, you got to get zeros. You get it to force zeros to occur on the boundary, for example, of the surface. That's a very special curve. I don't know. I think about that, but I don't. I have to think about how to get a mechanism that's going to make that happen if you don't have ergodicity.
Other questions? Can you prove that the diameter of the nodal domain tends to 0?
It doesn't. No.
But
so
for the density 1?
Well, density 1 though of what? Of the nodal domains themselves?
There is a subsequence of density 1 for which the diameter of the domains tends to 0.
I don't think that's actually going to turn out to be true. So that is to say, so first of all, density 1 refers to the eigenfunctions, and each eigenfunction has many, many nodal domains. But the physicists here basically, our picture of what they look like is random spherical harmonics. Most of the nodal domains are really small. They're basically of size 1 over lambda, maybe 2 over lambda, 3 over lambda, 4, small number over lambda. But there are supposed to be a certain number of what are called percolating nodal lines, which actually their length, their diameter doesn't shrink as lambda tends to infinity. It's completely mysterious to me how many such nodal components there are. But there's a guy, Ilyashenko, who wrote a very physics article about percolation. And there are various physics conjectures that tell you that there should be some percolating nodal components which do not shrink. Schramm had the feeling that this was going to be an example of an SLE4 curve. So it's really way beyond any technique I know to answer that question, but
in fact, if you're considering just one domain among all of them, it looks to me like it's for all the eigenvalues, the diameter should not, of at least one domain shouldn't tend to 0, because when you take one nodal domain, there should be another nodal domain that bounds it. There should be another nodal domain that bounds it. And so you
right.
from one small domain here to one.
Yeah, that's a good point.
You cannot do it without
right.
being of
large diameter. That's a good point. Yeah.
It's a compact manifold.
Yeah, but he's right. Even if you imagine making some kind of cheese, what would it be, a Swiss cheese? By removing all these little nodal components that are really small, you have to get something left over which is connected. So In
this case, because of orthogonality, these small domains they must be very high, very big.
The eigenvalue is large, yeah.
Eigenfunctions.
Yeah.
If you have the stable big domain, in this case, in small domains, it must be very big to compensate because of orthogonality. But it's impossible to them to go very high.
I don't think, even for random circle harmonics, which is much easier to study than actual eigenfunctions, and yet still extremely hard, I don't know, if the experts have even proved the existence of nodal domains with a big macroscopic size. I know that Soden told me that he expects only one. I have no idea why.
What's the question? Two. First is just a general remark. If you want to observe experimental nodal domains, you can go centuries before the quantum mechanics.
Yes, that's true.
And there was an experiment of a iron clad near sand.
You mean Chladni? Chladni goes back to 1800. In fact, it's a funny historical remark, but the problem that I'm discussing was actually invented by Napoleon. Chladni in 1800, he was like half scientist and half like circus performer. And he used to go around entertaining the nobility by, bowing these things and getting nodal domains and entertaining them with the pictures. So he had an audience with Napoleon. in 1800. Napoleon was a very good mathematician. Did you know? I mean, how did Napoleon become such an important figure? It is by being the best mathematician in his artillery school. He was outstanding. And so it was France, you know, they promoted people who were really good at math. So in any case, he saw Chladni did a square, and then Chladni did a disk. And Napoleon wasn't impressed at all. He said, you can separate variables in these problems and you can easily figure out the nodal domains. So Chladni basically asked him in some exasperation, you know, what would you like me to do? So Napoleon told him, well, you know, it's easy to figure out the nodal domain for a square. It's easy to figure it out for a disk. Why don't you cut the disk in half, put one over here, and one over here. Now tell me what the nodal domains look like. So it's a true story. And Napoleon invented the Bunimovich Stadium. And he invented a stadium which has ergodic dynamics, and he stated the problem that we're discussing in this talk. He also, by the way, instituted a prize of 5,000 gold Napoleons for anybody who could answer it. I'm not kidding. And Sophie Germain or something, won it. But for some biharmonic equation, it had nothing to do with nodal domains. So unfortunately, the prize money's gone.
All right. Let's thank the speaker again.